Today we are going to see some concepts of CFL and non-CFL. Out of that, today we are going to cover pumping lemma for regular languages and context-free languages. First of all, we will see what is meant by pumping lemma. Pumping lemma is nothing but, in simple terms, this means that if a string V is pumped, that is, if V is inserted any number of times, the resultant string is remains same in given regular language. Suppose we are considering regular language, then it comes under the regular language, and if we are considering context free language, then that V is belonging to that context free language. So according to this pumping lemma, it is defined for mainly two parts. First one is regular language and second one is context free language. So first we will see pumping lemma for regular language. For any regular language, suppose we are considering regular language L1, there exists number of integers which are comes under the n. Suppose we have considered n is an integer n is an integer. Then another one case that x, small x is nothing but the string which is belonging to given regular language or context free language. Now we have considered here regular language L1 and x is belonging to L, where mod of x is always greater than or equal to n, because n is nothing but our integer value and x is nothing but the string which belongs to language L1, that we have considered it as a regular language. And after that there exists u, v and w which are also belongs to given string, that is x, and that string is generated by given input set. That is, suppose there are two values in input set, summation is equal to 0 1. In that case uv and w are belonging to that input alphabet set, that is 0 1. Now we will prove it that such that x is equal to u, v and w, where mod of uv is less than or equal to n. This is our first condition. This is our first case. Then second case is what? Mod of v greater than or equal to 1, or you can write it as mod of v greater than 0. Meaning of both the statement is same. So this is the second condition which must be satisfied by our given regular language. And for all I greater than or equal to 0, where u v raised to I w, and that I is nothing but value which we have considered over here. Whenever we are replacing values of v in terms of I, in that case that string is must be belongs to given regular language, and this one is our third condition. And if any language any language satisfy these three conditions, then that language is considered as regular language. Otherwise, that language is not a regular language. So, in simple terms, this means that if a string V is pumped, that is, V is inserted only number of times, the resultant string still remains in L. Pumping lemma is used as proof for irregularity of a language. Thus, if a language is regular, it always satisfies pumping lemma, otherwise not. If there exists at least one string made from this pumping lemma which is not in L, then that L is surely not a regular language. So, this is the proof for pumping lemma for regular language. Then second case is what? Context free language. So we will see proof for context free language. So if we have considered for regular language, we have considered three values, that is U, V and W. But for context free language, we will consider total 5 language. So second part. Second one is context free language. So for context free language, we will consider L is our context free language. N is any integer. L is our CFL. N is integer. So that for any U belongs to given context free language, that is L. After that, for satisfying all these conditions, we have to check modulus operator. Mod of U is greater than or equal to N. First we have to check that condition. There are strings we have to consider here as V, W, X, Y and Z. We have to check these 5 strings which are the part of given string, that is U. If that part is satisfied, then that total string is comes under the given context free language. For satisfying these conditions, we require 4 possibilities. First one, U is equal to V, W, X, Y, Z. This is our first case. Then mod of WY greater than 0, which is our second case. Then mod of WXY is less than or equal to N. This is our third case. And last case is for any M is greater than or equal to 0, then V W raised to N X Y raised to N Z belongs to given language. So this is our last case. So if context free language, what a string we have considered from context free language, satisfy these 4 cases, then and then only our language is context free language. Otherwise it is a non-context free language. We can find a CFG in context normal form, Chomsky normal form, that generates L is equal to set of null strings. If we let P be the number of variables in the given grammar and N is equal to 2 raised to P plus 1, the result is an immediate consequent of theorem. So this is nothing but proof of regular language and context free language with the help of pumping lemma. So for understanding it, we will check some examples. First one, So we will go for one example. Prove that the language of palindrome over the input alphabet set 0 1 is not regular. For that we have to use pumping lemma to solve such a types of problems. Consider L be the language nothing but palindrome over the input alphabet set 0, 1. Then consider X is the string which belongs to given language, that is L. N is an integer value. N is integer. Now we will consider one palindrome number from this given input alphabet set 0, 1. Suppose we have considered one palindrome number 0 raised to 4, 1, 0 raised to 4. Now check, is it palindrome or not? Yes, is it palindrome? So we can consider, and by using this string we can find out whether given language is regular or not. So we are considering it as a x. X is equal to 0 raised to 4, 1, 0 raised to 4. This is the palindrome number. Now consider, we have to consider three parts. First one is V. First one is U, then V, and then W. So we will consider first U is equal to, we have to divide it into three parts. So we can make our calculation as we have seen in our pumping lemma explanation. So first we will divide it into three different parts, 4 zeros, 1 and again 4 zeros. So we will divide it into three parts. U is equal to, this is small u is equal to, suppose we have considered 3 zeros, then V is equal to 0, 1, 0 and W is equal to remaining 3 zeros. After that we have to satisfy these modulus operations. First of all, check whether given string is greater than or equal to n or not. Now here our n is nothing but this 4. So this is nothing but totally 9 values are there. So x is greater than n. Then consider mod of uv is less than or equal to n. Now check. Mod of uv contains u is nothing but 3 zeros and v is nothing but 0, 1, 0. Whether its length is less than or equal to n? No, its length is not less than or equal to n, because here n is nothing but this total string. Now check whether it is less than or equal to n. If we have considered x, then it is true. So our first condition is get satisfied. Then our second condition is what? Mod of v greater than or equal to 1. Now check. Mod of v is what? 0, 1, 0 is greater than or equal to 1? Yes. So mod of v is also greater than or equal to 1. So we have satisfied second condition also. Then third condition. Suppose we have considered as per our pumping lemma I is equal greater than or equal to 0. Suppose we have considered I is equal to 3. In that case our values of u, v raised to I and w, we have to check this value. I is u is equal to triple zero. Value of v is 010, and if we have taken its third value, it means rotation of these three values means 0 1 0, again 0 1 0, and again 0 1 0, and w is nothing but 0 0 0. Now check whether this string is palindrome or not. If we have started over here from left to right and right to left, whether that string is get satisfied or not. Here we are scanning from this side to this side. Check whether here four zeros are there, so we will write here four zeros. After that one is there, then two zeros, again one is there, again two zeros, again one, and after that four zeros. Now check whether string is get satisfied. Yes. So third condition is get also satisfied. But whenever we are considering value of value of I is 0, in that case what will happen? In that case also our string is get satisfied, and whenever we are considering it as a 2, in that case what will happen? Here whenever we are considered value of I is equal to 2, our string is become as 30, then 010, 010, and again 3 zeros. But we have divided our string it in equal parts, and suppose whenever we are dividing it into unequal parts, in that case this situation may not be possible. We will see that part also. U is equal to, suppose we have divided into two parts, U is equal to 00, V is equal to 0 1, and W is equal to W is equal to remaining 4 zeros. Now check, can we satisfy this condition? No, because whenever we are writing such a part, what will happen? First, U is nothing but 00, value of I is 3. So here value of I is 3. So while solving such an example, here V become as 001, 001, 001, and W's remain as it is. Now check, is it possible to take its reverse? Check it. 4 zeros. We are considering from right to left. 4 zeros, then 1, again 001, 001, and 4 times 0. So according to that, whether our given language is palindrome or not. Whenever we are considering for such examples, yes, it is a regular, but we have changed its example. It may be possible that given language is not a regular. Next part is we have to check given language is context free language or not. We have to check second example for context free languages. See, suppose we have considered L is equal to A raised to I, B raised to I, and C raised to I, such that I is greater than or equal to 0. This is our given language. We have to check is it CFL or not. So for proving such a language, we need to find out pumping lemma for context free languages. According to context free languages, first we have to consider one string, that is U, and after that we have to consider again 5 strings, that is V, W, X, Y, and Z, and then we will start our explanation. First of all, we have to consider u. Suppose n is equal to, this is small n is equal to, suppose 3 is there. Then u is equal to a raised to n, b raised to n, c raised to n. So according to that, it will become as a cube, b cube, c cube. It means a raised to 3, b raised to 3, c raised to 3. So the string become as triple, the string is become as triple A, triple B, triple C. So we have to divide it into 5 parts, that is V, W, X, Y and Z. Suppose we have considered V is equal to, double A will be there, then W is equal to AB, X is equal to BB, Y is equal to double C and Z is equal to remaining one value, that is C. We have divided this string into 5 different parts, V, W, X, Y and Z. Check whether 3A, 3B and 3C's are there. Okay, next. Now we are moving towards our 4 conditions of pumping lemma for proving context-free language. In that, first condition is what? Mod of WXY less than or equal to N. Here WXY are nothing but AB, BB and CC is equal to, mod operation of these values is nothing but 6. Whether that 6 is less than or equal to N? No, because N is equal to, right now we have considered N is equal to 2. So here first condition is not satisfied. Then we are moving towards second condition. Second condition is nothing but the mod of WY greater than 0. Now check, mod of WY is nothing but, W is AB and Y is nothing but CC, which is equal to 4. 4 is greater than 0. So second condition is satisfied. Then our third condition is what? Suppose we have considered I is equal to 2. In that case, we W raised to I, X, Y raised to I and Z is belongs to L, is belongs to L. Now we will replace our V, W, X, Y, Z with our given string, that is V is equal to AA, W raised to I, W is AB and AB raised to 2 is equal to AB, AB. Then X is as it is BB, then Y raised to I means CC raised to 2 means 4 values of C and last one is Z. That string does not belong to given language. So our third condition is get not satisfied. And last stage is what? We have to verify whether four values are get satisfied or not. If not satisfied, out of these 4 conditions, single condition is not satisfied, then our given string is not a context-free language. So output of this means answer of this example is given language is not a context-free language.